Hello and welcome everybody to this next installment of the laboratory software. Got to have that long pause for my introduction. It's like a trademark or something. I don't know. I just like doing it, but it's Laz. Who else would it be doing this? I got the whole market cornered on reviewing laboratory software for geotechnical engineering. What can I say? Well, the older versions of stuff, at least, that I can get my hands on. Anyway, so in this segment, in case if, obviously if you're watching the video, in case the title hasn't told you what is going on here, we're going to be covering over hydrometer analysis of soils specifically. So, like with anything, can't really start off with all the fun without a background story, right? Education's not meant to be fun. It's only fun for the person that enjoys it. That's how it always is, right? And especially since I don't have anything to show and or demonstrate to you because, reasons. Mostly, mostly if I see an uptick in people really liking this or people really asking questions of, hey, so, you showed us all this data. How is this test actually performed? Then, I might be more willing to show that to you and how it goes and whatnot. I just don't have a lot of cameras and stuff. So, all I really have is my phone. Obviously, I don't care about showing who I am or my face because I have vlogs that I've posted from years back. So, obviously I don't have a problem with that. But anyways, enough of me getting off topic here. Laz's favorite thing to do, rambling and then getting off topic. Let's talk about hydrometers for a little bit. So, hydrometers overall, it's pretty much determining specific gravity of a material within a liquid itself. Most of the time, the liquid used is water, and usually the water, it's usually demineralized or deionized water. So distilled water is usually used because all those minerals and particulates can disturb the actual hydrometer reading. So, so the way how the hydrometer test works, at least for soil, because you could do hydrometer testing on alcohol. That's how they generally determine alcohol content. A hydrometer in its most basicest, that's not even a fucking word, in its most basic form is you're determining specific gravity of your suspended particles within your liquid, which in this case, this is going to be soil particulates suspended in deionized water or distilled water. There's a lot of different ways on how they like to say water without minerals. So, that's usually the water. You could buy this in any grocery store, at least if you're here in America. You could buy it at any grocery store, and it'll usually say for use for appliances. That's the kind of water that you would want to use for this test, pretty much. Or unless if you have a built-in distillery or something like that, then hey, that's perfectly fine as well. Because you're going to calibrate your hydrometer and whatnot, obviously for use or before use, and so the thing with this test is what this test determines is what is your percent silts and your percent clays that is passing your 200. So obviously, for many videos back, I've already talked about a 200 wash and what it is and whatnot. So it's for all those particulates that pass through that 200. It really determines if you have, let's say, 4% passing your 200 sieve. This is a very horrible example because you really wouldn't do a hydrometer analysis on anything that low passing your 200 wash, but I'm only making it a small simple number because math's easier in my head that way. So let's say you had 2.4% of it was silts, and then you had 1.8% that was clays. That's what a hydrometer analysis does. Sometimes they call this test a particle size distribution. You know, and it's usually attached with your sieve analysis at the very end that would show extra points that would show the millimeter sized particulates that the hydrometer was able to determine. So as I say so a lot, I hate that I do that sometimes. Kind of like self-conscious moment. You're welcome. So the thing here is clays are denser than silts. So clays will settle faster in for your hydrometer test than silts will. So let's say, I'm just giving a general example and whatnot. Let's say you had your, sorry, I bumped into the mic there. Let's say you had a hydrometer reading of 15 at 5 minutes. So you take a reading at 5 minutes, and you had a hydrometer reading of 15. And then at 30 minutes, you might have a reading of like 12. So what that indicates is that you have a lot of clays, because while your clays are suspended in the water, it's going to settle fast. Kind of like with sands. The denser something is in water, the faster it's going to settle. And that's all the hydrometer is doing. It's just telling you how fast things are settling within a given time parameter, whether if it's by the specification or by an engineer, or job requirement, whatever that may be. That's the whole idea of this test. There's preparation to this. There's a lot of steps to this whole test and whatnot that you would do before you would get to the reporting part that, I am just going to kind of cover briefly here because I really don't want to bore you. So before that, let me take a sip of some liquid encouragement. Okay, so typically with a hydrometer test, you're testing it on soils, and your soils can have aggregates. And remember that keyword aggregate just means rocks in general. So with a hydrometer, it really determines what your particle size distribution is going to be, which is the reason why they call it most of the time, at least the fancier terms, when somebody gets a report, you might get a particle size distribution report or curve that's going to show you everything that makes up that composition of that soil tested. You test everything for this. The difference being is that for your actual hydrometer portion of your test, you're only testing material either passing your number 4 sieve or your number 10 sieve. And that's kind of the optional thing. But it also depends on your test method too. I don't want to dig too deep. So the number 4 and the number 10 depends if you're doing AASHTO's T88 specification or if you're doing the discontinued ASTM D422. That's been replaced by other test methods that technically our laboratory doesn't perform currently due to equipment limitations, as well as this test isn't really requested enough to justify to purchase said equipment to meet the newer specifications. And there's still a little bit of animosity. I think the animosity is dying down, with me being in the industry, with engineers not really liking the new test method, because technically, for what I'm going to show you report-wise, they broke that up where it's 2 different reports for some reason. And I don't know, with it being 2 reports, because I've never seen an official one, if everything combines together to make one particle size curve, or if it's literally, hey, here's your hydrometer curve, and then here's your sieve curve, pretty much. And then you put it together, or however. I know that was like the biggest animosity before. Not that engineers are against this new method. I hear it's easier to do, But it's like I said, like you need certain equipment in order to do it. Like I think we have probably like 70 or 80% of it, but we need that. You have to have all of it to do this. This isn't a, well, we can just finagle around this, or, we can work with what we have. No, you have to have everything to do the newer test method, which that I'm not really going to get into details. Excuse me. Sorry. So as Laz continues his TED talk here, so you get your sample, you're going to split it. It has to be air dried. So, where if it's in front of a fan, nothing above either 140 degrees Fahrenheit or 60 degrees Celsius. That's your maximum temperature that you can dry your sample in a convection oven. If you were to choose that, I typically use the convection oven because then it's a good guaranteed dry. I mean, it doesn't have to be bone dry, but you really don't want it where it can still clod together, because then it's harder to process the sample when splitting it over a sieve. That's the reason why they have that set. So, obviously you'll do that depending on your material type. So where if it's a sand, it could really only fall in two categories. It's either sands or silts and clays. And if it's sands, and this is for everything I'm kind of covering, this is just focusing on AASHTO's T88 because that's the current active standard for doing hydrometers that we do. Even though we can still do ASTM D422, it's a discontinued method by ASTM. And while some engineers will still ask for it, we can still do it. And usually if the engineer requests it, they know it's discontinued and everything is noted in the report. Hey, this is a discontinued test method that's following this and that or whatever. It's engineer's choice in order to get the data that they need in order to engineer things properly, correct? So it's that ultimately at the end of the day. So obviously you do that, you prep your material depending on your material type, whatever your initial classification that's going to fall in, which that's just a visual classification to determine, does it seem to be more sandy or does it seem to be more clay or silt, which if it requires a full classification test that we've already covered in a different video, if you're able to do Atterberg limits and the such, then that's going to be a clay and or silt. So usually for clays and or silts, you're going to test 65 grams of material for your actual hydrometer tested portion. And then, of course, your sands, you want 100 grams tested for your hydrometer portion. And, you get that. You're gonna make a sodium hexametaphosphate solution, as they like to call stock solution. It's pretty much the bare bone components in soap. It just makes water wetter, so all the silts and clays and I don't want to say unmentionables, but unmentionables that are attached to actual sand particles or particulates can actually come off those particulates and become suspended and or just become detached, so you can determine how much is going to pass your 200. But that's a lot further down the line as we go through this big checklist. So you'll make your stock solution, you'll add it to a beaker, you add a set amount. Technically it's 125 milliliters of stock solution. You stir it, you let it sit for 12 hours. After 12 hours, you're going to throw it in your dispersion cup, which is pretty much a commercial grade shake mixer that is capable of doing 10,000 RPMs. After that, and you do that for 1 minute in your mechanical shake mixer, then you're going to pour it into a 1,000 milliliter glass cylinder. And then after, when you pour your material, you're going to clean out your cup, make sure you get everything out in there, and then you're going to fill the rest of your cylinder up with your distilled water. You don't have to fill it up all the way because now you're going to shake it. So you're going to invert it. You're going to invert it horizontally. So all the particulates are getting suspended for about 60 seconds, and then as soon as you set that cylinder down, your time starts. This is a time test, by the way. So, like I kind of indicated before, it's up to the engineer to determine what time increments that they need, because depending on the time, kind of focuses on what set size particulate you might be examining at that time when your hydrometer is submerged, or really floating in your sample and whatnot. So if somebody wants to know, hey, I want to know, the particulate size of like 0.0030 millimeters, that might be a specified time. Like you might get that in, I don't know, I'm just thinking off the top of my head, like 20 minutes or something like that. Like you'll get that however those suspension, or at that point moment of the particle suspension as it's settling, that's going to capture most of that specific size material in itself. So it's really up to engineers' discretion. Obviously, the specifications themselves has a times table, or hey, you're going to take readings at X amount of minutes, because this whole test is done in minutes. Usually after 24 hours, which is 1,440 minutes, you take one final reading, and of course, with every reading, I almost forgot to add this. With every reading, you're also going to take a temperature, because temperature is important, because that changes the specific gravity of the water. Like I indicated before, it's pretty much specific gravity is what this is. It's another form of specific gravity is what doing a hydrometer test is ultimately at the end of the day. It just depends on what type of hydrometer that you have, which I'll cover into that maybe a little bit more in detail when we actually get to the program itself. So you do all that. After when you take your final reading, sometimes engineers can be, I don't want to say difficult, but sometimes they might want a 48-hour reading too. So, you'll take a 24-hour reading, whatever your final reading is that is designated by the engineer specification or plans, project plans. You follow it according to that. You get all that data with your sample itself that's still in the cylinder. So remember, what's in your cylinder is either your sand slurry or your clay silt slurry with your sodium hex stock solution that you added 125 mils, and then the rest of it being distilled water. Now you're going to grab your cylinder, and then you're going to pour that over a 200 sieve without spilling any material. Wash it over your 200 sieve, get all your material, retain your 200 sieve, and then you're going to throw that in a 230 degree oven or 110 degree Celsius oven, and you're just going to let it dry until the next day, pull it out. Then you're going to do your sieve analysis that's going to finish the rest of your curve. Now, that also accounts for coarse particles, which, coarse particles, I don't want to say is tricky or whatever, but it's something that people always mess up that I've noticed from me working in this industry. People get really, really confused when they have to deal with coarse particles. And, kind of like what I've already stated quite a few times for just going over the test methods in general, virtually every single test method, at least within the not civil engineering, geotechnical engineering field, any of those test methods always has your nominal aggregate size or a nominal sample size or your minimum sample size or something. Obviously, I stated some of those. But, if you have anything that, let's say, you collect a soil sample and it has 3-inch rock in it, your specification is going to tell you, hey, your minimum sample size is going to be this many kilograms or pounds that you're going to process. And that's what you would initially process. That whole sample, and then out of processing that whole sample, that's where you get your subset sample for your hydrometer test. So whether if it appears to be more sandy, then you'll get 100 grams of that sand. And you can have 5,000 grams of that sand left over. All you need is 100 grams. You're just going to properly split it to get an unbiased account for what you're going to test. So obviously, if you have coarse particles, you're also going to add it on there. That's technically a separate sieve analysis. Everybody's all over the place where if you should wash that aggregate or not. I mean, obviously, you eyeball it. If you're the technician, you're going to eyeball it. I'm not trying to treat this into a training session thing neither, or a soapbox thing for me to rant on about all this. But I can't tell you, from my experience, my 18 years of doing this, I've had an engineer call me out once when I'm doing this guy a favor. Hey, I need this hydrometer test. I did the hydrometer test. The guy looked at it, and it's like, okay, this looks good, because I sent him a preliminary report. But then he had to put it into his system, and then he got very confused on how to put it into his system, where he's like, I don't understand how you have values of here and here for your raw data, and then yet your preliminary report that you sent me looks perfect. Like, how did you come up with this? And obviously I told him, well, there was coarse aggregate, so there was material greater than number 10, because I split mine personally on my number 10 sieve. I had greater particles, so that's a completely different sieve analysis that has to be combined with the current sieve analysis. So you have two different values that you have to work with that needs to combine into one seamless thing for it to work, which you can get that because, kind of like with my earlier example, let's say you had 3-inch rock and you needed like 5,000 grams of material or 5 kilograms of material to process. Okay, well, everything that's coarse material all the way up to that number 10 is going to count that 5,000 gram marker. So I can give you percentages like 89% passing like the 3-inch sieve or the 3/8 sieve or something like that. I'm able to use that value in order to get you that value. And then obviously everything passing the number 10, I'm going to use whatever my value that I use for my beaker. It's really simple. So long story short, the phone call ultimately ended with the engineer telling me, well, out of the 30 years of me doing this, and I teach a remedial class on engineering, at the whatever campus and whatnot. It's like, I've never heard this in my entire life. And obviously I'm thinking to myself, well, if you knew all this, why didn't you do it? Why didn't you do it? Why didn't you have your facility do it? Why didn't you push to get your facility accredited if you didn't like how I did the test? So you could say I'm extremely cynical when it comes to hydrometers, because when I get chewed out that I'm doing something wrong, when I'm double checking and triple checking that I'm doing it right, that's not right. It holds very dear to me. And I'm not saying I'm not prone to mistakes. I am. I'm very prone to mistakes. But when I'm following exactly what the spec's telling me to do, because I had particles that were bigger than what you wanted for your hydrometer tests. Remember, it's a particle size distribution report. Anything that is part of that sample must be on that report. You can have 6-inch rock. It needs to be on that report. If that was part of your sample, you encountered 6-inch rock, that's part of the report. And that's the thing that I think a lot of laboratories and engineers fail to recognize sometimes. Anyways, that rant is over. So that's pretty much the overall gist of doing a hydrometer test. So now, since I've bored you, we can really get into the software. So let me take another sip of liquid encouragement. So I am going to say this. Technically, a couple of weeks ago, I did use this. I used it because, I was on PTO, And obviously, my job called me and, hey, we had these issues with hydrometers. And of course, I don't have what they're using there. Yes, they have geosystems, but the version that I have is very old. And obviously, when I tried doing hydrometers here for them, it kept crashing. So, that was kind of fun. So I kind of used the the soil mechanics software that came with it, and so it works. It's definitely something that I am not used to. It's very extremely simplified, which totally makes sense for the idea and the practice of this. So technically, I did get my hands on that a little more than I thought it was going to be. So it is going to kind of ruin the rest of the video because I kind of have an idea on what I'm doing, and I know everything else was, well, let's just figure it out as we go, and that was supposed to be the fun and joy and rapture of these videos. So I'm sorry if I ruined that. So the rest of the video might be quick from this point. Here's your big disclaimer warning right now, okay? Woo 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 woo, whatever in the world. So I do want to give that. I did technically play around. Well, I tried double checking some results, but ultimately, I just had to hand calculate it, and it sucked. It sucked a lot. It took me 3 hours. 3 hours while I was off to do that, by the way. So, it's all right. It's my vacation. How else would I spend that? All right. So here we are. We're in our soil mechanics laboratory tests. As I kept rambling, as I kept clicking on things. I mean, come on, guys. If you've been watching this already, if you haven't already known, this is come on. So, anyways, this is our hydrometer analysis portion for this test, and so just like everything else. So we got a description of soil. For this, we're just going to say clay sand. Sample number is whatever the hell you want to use. It isn't necessary. It's whatever your thing is. We'll say backyard hole for a location. I didn't technically test anything. I haven't tested any soils at my house the entire time I've been living here, by the way. Okay, so let's see here. So I think that's specific gravity. We're not going to fill that in just yet. So here we go. So kind of like what I talked about very briefly, you do have, when it comes to soils, you do have two different kind of hydrometer types. And your hydrometer types do vary greatly, and it's extremely important to know what type that you use. So you have a 152-H and you have a 151-H. And I can tell you, most of the time, everybody's using a 152-H, which a 152-H hydrometer, technically, it's shaped, I believe they're both shaped a little bit differently, but the biggest thing is with a 152-H, it gives you a number value, a whole number value. Let me focus on whole number value here. And I feel like I've talked about this before in one of the other videos. A whole number value. Actually, I probably talked about this a little bit in the sieve analysis for geosystems, because it does have a hydrometer section. It's just we didn't get into it because I didn't have any data for a hydrometer. Now I have data for a hydrometer. But I can tell you we're not going to cover into the geosystems one because it's going to crash. I know it's going to crash every time. As well as if I didn't cover it in geosystems, this was background notes, this whole video, then I wouldn't be covering it here because it'd be double the work. I'm trying to make this easy, everyone. So So for your 152 hydrometer, it has whole numbers with lines on it, so you know what your reading is. And then, of course, I didn't cover this while I was explaining the whole process of the test, but technically, when you take your reading, you're going to put your hydrometer in your 1,000 milliliter cylinder, and then you're going to take your reading at the top of the meniscus of the water. And I know we talked about meniscuses before. Remember, meniscus is the curvature of water. That's that weird curvature thing that you see. Like if you had a clear glass and you see that weird curvature thing where it doesn't look flat, that's called a meniscus. So you're going to read at the top of that where it's going to touch your line on your hydrometer, and that's going to be your reading. And then as you take your readings, you are also going to record a temperature because specific gravity of water. You know, obviously, if your water is hotter or colder than it needs to be, then it's going to greatly affect your position of where your hydrometer could be, where you might need to apply a correction on that, which technically you would have already done that from calibrating your hydrometer initially. Okay, so for the 151 model, I never seen a 151 to be honest, but I've always heard that either it just states a specific gravity on it, so you might see like 1.015 or something like that, and you'd still take the reading the same way. It's just your values are going to be different, and also I believe how it's molded and how it's shaped is different. I know when it comes to measuring alcohol content for like beer and whatnot, those kind of hydrometers are shaped vastly different than what a soil hydrometer looks like. And like, look, if you don't know anything I'm talking about, you can Google ASTM soil hydrometer, ASTM, you know, 151-H hydrometer, 152-H hydrometer. You know, I'm not trying to get into hairy, even though I'm really am getting into hairy details. I'm not trying to get any more into hairier details than what I've already have done. So, okay, I think now we can really get into the testing portion of this. So, you know, for the example that I have here, we use a 152-H hydrometer. So we need a dry weight of our soil, which is known as WS in grams. So for this soil type, we did let's see here, and there is I know I'm slowly coming to the realization that there is no hydroscopic correction on this, which is funny because did I not say I just used this a couple of weeks ago? But I had so many things open on my computer. I can't tell you how many different things I was using in order to figure out answers for those guys while I was off. So for my example here, we're just going to say we have, if a calculator will open anywhere, I guess it won't open anywhere. Okay, how about now? Gonna open maybe here. Okay, there we go. Somewhere, because I don't think the calculator macro works too well in XP. It should, but sometimes it doesn't, because I do have a newer keyboard. So, okay, let's do some quick math here. So I do have a written down corrected value from my hygroscopic moisture, because you're also going to get a hygroscopic moisture because your material was air dried. So there still is moisture in your material, especially if it's clays or silts, because it can hold a lot of moisture. And, you know, you don't want to oven dry it because, you know, once when you get that moisture out of it, you can never put it back in, you know. At least not through natural means, you're not going to be able to put that moisture that you lost back into the material, you know. it takes decades for it to get back to where it was again in a natural environment. So, okay, so this one, technically I already have calculated, so we're going to do some quick math here. So with my sample and beaker, we had 193 and 186, Jesus, 193.86 grams of material, and my beaker weight was 93.56. So we processed 100.3 grams of material for the hydrometer. There we go. Okay, so this one here, which is, this is where I say Geosystems is better, because technically Geosystems, you can put in your calibration for a over time, right? I mean, even inside a building. So fortunately for us for the example, but even if it wasn't on the example I had, this one will only stick to one temperature for your correction, for what the readings you had for your test. That's going to be also utilized for your correction. So for this one, this is 22 degrees Celsius. Okay, so we got our meniscus correction. This one I'm just going to have to ballpark off the top of my head because I do not have a calibration record of our hydrometer on hand because, that's all at work. Or maybe, did I write it down anywhere? I did not write it down anywhere on any of my notes while I was off, which is all right. Like I said, I was going to ballpark it anyways, So your correction factor, this is the idea. When you calibrate this, so when you calibrate your hydrometer, what you're pretty much doing is you're going to make your sodium hex solution. So for that, that's 40 grams per every liter is the solution. That's your ratio that you're going to do for the solution. And technically, you're going to get your 1,000 milliliter glass cylinder that you're going to use in general. And you put your hydrometer in there, and then you're going to check and see what reading you're going to get. Because technically, your sodium hex is a particulate that is going to be in the water. So it's really determining with the sodium hex concentration that you're adding, how much is that offsetting your hydrometer reading? And then obviously with temperature, it's going to affect how much it's going to offset your reading even more. The cooler it is, well, the denser your water is going to get. So that means, you're probably going to see values that are going to be higher. Yes, higher. I had to think about that for a minute. Yes, so if it's cooler, it's going to densify, and I don't know why I threw myself off because I've only been talking about specific gravity. So technically your zero value on your hydrometer, if you haven't already Googled this by now, is at the top of your stem of your hydrometer, and then your higher values are more closer to the bulb portion of your hydrometer. And really at the bottom of your stem before it turns into the bulb portion. And technically, the higher the value, the higher the specific gravity is going to be. So, if the specific gravity is higher, that means it's denser. And, what's dense? Ice. Ice is dense, right? Geez, I can't believe I just kind of had to think about that for a minute. Good Lord. You see, none of these are scripted. Makes it even more fun. So our meniscus correction, kind of like what I was talking about. So, your sodium hex is a particulate that is in your distilled water, so it's going to displace your hydrometer. So technically, even though your if you remember, or if you try to do a percentage or ratio, because technically there's only, Let's figure that out. 125 divided by 1,000. This is, I'm going to feel, it's 12.5%. So I can't believe I'm an idiot. I couldn't do that in my head. So understand, out of that 1,000 milliliter beaker or cylinder, it's not a beaker, out of that 1,000 milliliter cylinder, only 12.5% of that is your sodium hex mix. That is your 40 grams to every liter that you're going to make, that you're going to add to your soil slurry solution that you didn't add. Then you add the water. But even with that kind of concentration, it's still going to displace your hydrometer because it's very sensitive to particulates. So, when you calibrate it, you might do, and you'll do it at a temperature gradient that your facility can maintain. So if your temperature gradient is anywhere from 20 degrees to 25 degrees Celsius, then you want to make sure that you hit those points. It's anywhere where your hydrometer is going to be exposed to that temperature because it's going to change the density of the water. So if the density of the water changes, then your hydrometer reading is also going to change with your sodium hex solution that's in there. So you could say at 22 degrees Celsius, you might get a reading of, let's say, like 4. Let's just say 4. So this is with no soil sample, no nothing. This is just your sodium hex solution inside the water, and you got your water temperature to 22 degrees Celsius, and you had a reading of 4 on your hydrometer at the top of your meniscus. Then that's part of your correction. So technically, if you were to get a reading of, let's say, 14 at 22 degrees Celsius, and if it was 4, then what that means is technically you're going to subtract 4 from your actual reading. And then this is where your actual reading is going to be 10. Because you're subtracting 4 from that, because technically the sodium hex in the water density has displaced your hydrometer reading higher. So, have I lost anybody yet? I'm pretty sure I've lost plenty of people. Speaking of losing people, let's talk about today's sponsor. That's nobody but me. As well as check to see how empty everything is. Okay, I'm not surprised. I've been very boring the whole time. Nobody ain't going to come to these things. Why I don't like my TED Talks. So that's that whole idea with doing a meniscus correction here. Okay, it's that. So this is where I gotta, this I'm going to be ballparking a lot. So here we got a temperature correction of like 2.15. We'll say 2.70. That should be our specific gravity. Because having a specific gravity is going to dial in where on the graph it's going to fall. It just makes it a lot more accurate for what your final report's going to look like. That's the idea. So let's see here. God, I hate trying to pull things out of my ass, but I don't know. I guess I'll just stick with the 4. We'll just say 4.0. So you also have a zero correction. Your zero correction is actually, I think that might have to be a negative number. I don't know. I know Geosystems, it's a negative number. I guess we'll see when I put in all the data. Okay, so your zero correction here. So for this one, I should be able to put 0.0 or just 0. And so, your hydrometer over time might get worn out or anything like that, where you might have to recorrect where your zero mark is going to be. Let's say, for example, you notice that your hydrometer is about, when it's just in plain distilled water, so you fill up your cylinder with your distilled water and you put your hydrometer in and you notice like, that's weird, because technically your hydrometer should be right at 0 because there's nothing in the water. There's nothing to displace that hydrometer whatsoever. And regardless of temperature, it should relatively stay at 0 unless it's like cold to freezing cold to boiling, to simmering to boiling hot water, then yeah, your hydrometer is probably going to be moving around. You might get a variation from that. So typically when you do this test, your hydrometer should be zeroed. Over time with use and whatnot, it may not be like that, or it might just be a manufacturing error. Maybe they didn't curve the glass just right when they put everything together. And you might notice when you put it in, kind of like what I said, it might be in between 0 to 1. Now, like I kind of ranted a little bit before, it's all whole numbers. So technically it should be to the nearest whole number. In that case, you could probably say 0.5. You could probably eyeball it a little bit, but really it should be to the whole number. But I mean, when it's coming to a zero factor, you definitely don't want to say, okay, well, since it's not 0 and it's not 1, I should probably just say 1. Well, remember, now that's going to make that 1, where technically if you have a reading of, let's say, 5.5 and you put down 1, now with your meniscus correction and then you saying 1, now it's just going to say, okay, so that was 0. When technically it should have been 0.5, which it would have rounded to 1 or just kept the 0.5. It just depends on your software. Also depends on the person. But I don't like eyeball. There's no half tick mark on your hydrometer. You can't say it's at the half mark. Okay? You can't, people. You can't. You could write everything in the YouTube comments or to me directly or whatever. You cannot put 2.5 as a reading unless your hydrometer physically shows it can do 2.5 or you have half tick marks. I cannot stand that so much. It's like, well, yeah, and I get that it was in between numbers, but guess what? It only reads to a whole number. Round to the whole number. How much closer is it to each number? Pick one. See, I get being accurate's important, so you'll do the half, but is it really half? Or is it more so like 2.65? Or is it 2.45 or 2.3? Or could it actually be two and a quarter? Do you see why I'm nitpicking so hard here? Like you can't do that. You don't want to do that because it can give you, it could completely change the fact of how much silts to clays that you have. And sometimes with this test, there are certain specifications that require, hey, this needs to only have this much silt and this much clay with this much passing to 200 sieve, like baseball clay. That's like the biggest thing out there that I've dealt with personally, that it needs to be within that specific sweet range for it to be accepted as baseball clay. So that's why. And trust me, it wasn't a bad experience for me. It's obvious common sense. There's no half tick mark. How are you going to say half? Well, if it's not a half, you don't know. It's a blank space between 4 to 5, and it's in between 4 to 5. Where is that water line closer to 4 or 5? Just say it's 4 or 5. But anyways, I know I ranted way too long for a zero correction factor. You see how passionate I am about this. Let me scream at you how passionate I am about hydrometers. And the funny part is I don't even think, to level with you, to be honest with you, I've maybe have done maybe a little over 100 out of the 18 years of me working in this industry. Now, granted, I'm in the great old state of Florida, so there's not a lot of clays and stuff, but still, for me to be as adamant as I am adamant as I am because it's common sense and practice. That's it. Okay. Whew. Okay, enough of that. Let's take another sip of liquid encouragement. And trust me, I'm not drunk. I'm far from it. I'm drunk on knowledge. But not on that to get as passionate as I am. I'm always passionate like that when it comes to hydrometers. So, anyways, it's Laz. Technically, it's this time is when I'm currently recording it and streaming it and whatnot. All right, so let's hope that I put everything in correctly. I can't remember if this needs to be a negative or not, which is crazy because I did this like less than 2 weeks ago. And enter friendly, let's see, 2 minutes, 5 minutes. Is this, no, it's arrow friendly. So 2, 5, 15, 30, 60, 250, and 1440. As you can see, it's all in minutes. So technically 2 minutes, 5 minutes, 15 minutes, 30 minutes, 60 minutes, that's an hour. 250 minutes, that's 4 hours and 10 minutes. And then 1,440 minutes is 24 hours. So, all right. So now this is going to report our hydrometer readings. So here we got 15, 15, 15, 14, 14, 14, and then 13. And then it just calculates everything out right over here off to the side. Now, technically, you have your L and A here, which this will let you, correct it, if you needed to do anything like that. Because also when you calibrate it, you can figure all that stuff out and whatnot. This just gives you relative numbers for what it can do for whatever values that you put in here. So, if I did say 0.0, I don't know if anything would change or not. Yeah, see, it would change. It's an old dated thing. As you can see, there's no such thing as an automatic refresh thing because, this program came out in 98. But as you can see, our temperature correction changed from us changing that and whatnot. Let's see 4.0, and if I did 15 again, see, it's drastically changing. So I think, which would make sense, this would have to be a negative value only because, we're taking that away from it. So, we do that, and then here's our plot here. So technically, this is what would come at the end of your 200 sieve and whatnot. So, you would have your grain size distribution curve would be here, then would connect, and then after your 200, you have this. And it should always settle like that. It should never go. It should either be at the level of your 200 with it dipping a little bit, or just a flat line across, but it should never like go back up or anything. It should never look like a weird backwards check mark or anything. So, if you ever happen to do this or are playing around with data yourself and you're like, oh yeah, that looks good. Yeah, no, it should look something like this. Kind of like what I said, this only focuses, this only focuses on just that in itself. So, yeah, and then there we go. That's it. So, I did all this talking for something that probably could have gotten done in, I don't even think 5 minutes. You're welcome. I'm glad that I was able to take up your time for that. So there we go. That, my friend, is overall a hydrometer analysis. At least the final ending portion. I would have already had an example together for you, but unfortunately, all the examples I have data like client information and whatnot, and obviously, I don't know who signs NDAs and not for my company, as well as if I'm even allowed to even show anything from my current company, unlike from my old company that has been absorbed, so it doesn't exist anymore. Which is the reason why I was able to show you Geosystems, this version of Geosystems. So, there's that. So, yeah, there we go. Let's take questions that probably aren't here. Let's see. So, we got that. Let's go to here. We got nobody else here. and I don't have any direct chats. So there we go. All right. So I think this is a good point of ending to end this video. It's been probably longer than it needed to be, but once again, it's trying to explain to any other person that's never experienced this before to get a rough idea. I know I don't have a lot of visuals and things like that. And it's like I said, I don't mind trying to do everything like that, but it's not like these are scripted. If these were scripted, I wouldn't even be streaming these. It's the fun of checking out programs that were used back then, and at least for my own personal nature, for me explaining it so you guys can experience it vicariously through me. You can see how well in the differences as you hear me struggle sometimes, if not all the time, doing this. Not like I'm not comfortable doing this, otherwise I wouldn't be doing this. So anyways, enough of me rambling. You guys heard enough of me as it is. I hope you enjoyed the video. If not, please let me know. There's YouTube comments. This is obviously going on YouTube. I know the site got updated, so comments are turned off for anything new that gets posted, so you won't be able to comment on this. But obviously, you have all my social medias. If there was people here on Telegram here, I'm on Telegram, I'm on Discord, I'm on Blue Sky and YouTube and everything and whatnot. But I'm going to end the video here, and I'll catch you guys next time. See ya.